If you take a look at what we did in chapter 7, you can see that we started out with the basics of confidence intervals, right? Like what is a confidence interval, margin of error, that kind of stuff. And then we looked at 4 different types of applications to the confidence interval. So we started with the mean, the average, right? The average of a sample set, and it was 1 sample. Then we looked at the mean of 2 samples. So you got 2 sets of data. Sometimes they're dependent or they're independent. Most of the time they're independent. Then we got done with means and we went to proportions, which was the proportion of success, P, right? Like the number of successes divided by the total number. And so we looked at finding the interval for proportions in 1 sample, and then we looked at the interval for proportions of 2 samples, okay? So all 4 of these involved intervals, like an upper bound and a lower bound, right? And then we subdivided it by first looking at means, 1 sample, 2 sample, and then looking at proportions, 1 sample, 2 sample, okay? So as we move to chapter 8, chapter 8 talks about hypothesis testing, or sometimes this is called inference. And we're going to look at what inference is, and then we're going to apply it to the same 4 situations that we had in chapter 7. So we're going to look at inference for a mean, just a single sample, and then inference for a mean given 2 samples. Then we're going to look at inference for a proportion, 1 sample, and then inference for a proportion with 2 samples. So the idea is once you wrap your head around what this hypothesis testing is, and that'll be kind of the tough part, the rest of it should be very closely related or even parallel what we did in chapter 7. So you're like, oh, okay, I'm looking for means and it's 2 samples. So this is what I got to do, right? Because you've already seen some of this. Because you've seen these 4 scenarios, it should be a little bit familiar to you. And so that's intentional. We designed the textbook and the flow of this course intentionally so that way these 4 things line up with chapter 7 and they line up with chapter 8. And so this is hypothesis testing. And hypothesis testing is where you make a hypothesis and then you go and you collect data and then you see if the data either supports your hypothesis or does not support your hypothesis. And there's kind of a backwards way that we go about talking about hypothesis testing. And so we start by reading through this. And hypothesis testing is critical to the scientific method. So when you're conducting experiments and you use the scientific method, which you probably first learned about like maybe back in 5th grade and then again in 7th or 8th grade science, we talked about the scientific method. And the idea is that things are never proven true. The scientific method says you can never prove something true. Gravity is a theory that's not proven true. So no one's been able to design an experiment that breaks our current understanding of gravity. Therefore, our understanding of gravity is not proven false yet. We can't actually prove it true. And that's the scientific method. And it's going to take a little while to wrap your brain around this, but you'll get there. So take a moment to reflect on this. A hypothesis is never proven true. Instead, it's only proven not false. And so there's a good analogy about this. If you think about playing King on the Mountain, remember King on the Mountain, like used to play it in elementary school where they'd have like a big snowbank and someone would get up on top of the snowbank and they were the king of the mountain. And then other people tried to push them off and then they'd become the king on the mountain. So an existing hypothesis, if you have an existing hypothesis, this is also called the null hypothesis. That's an existing hypothesis, an existing theory, and that is king of the mountain. So this king on the mountain, this existing hypothesis is constantly challenged by new experiments and alternative hypotheses, okay? And it will remain king of the mountain only if it's not proven false. Once this null hypothesis, the existing hypothesis, the king of the mountain, has been proven false, then it is dethroned from the mountain and the alternative hypothesis becomes the new king of the mountain. And so this is kind of how the scientific method works. You're current king of the mountain until someone comes along and proves you false. Then their alternative hypothesis becomes the new king of the mountain until someone else comes along and proves that false. So no one is ever proven true. No one says, yep, your theory is right. They can only be proven not false. That's how science works. And that's what we're going to do here. So the idea is we're going to have a null hypothesis. You're going to have an existing hypothesis. The existing hypothesis might be something like, we think that the average GPA of all college students is 3.5. That could be our null hypothesis. That's the existing theory. And what we'd like to do is suggest an alternative hypothesis. Our alternative hypothesis might be that the GPA is greater than 3.5, greater than 3.5. So then you'd go out, you'd get a sample, you'd collect some data, and you do an analysis on that data. You'd calculate some probabilities. And based on that data, you would either accept or reject the null hypothesis. Okay, and we'll walk you through all of this. So that's what's going on here. So there is a little bit of note about why we say fail to reject instead of accept. So you don't say we accept the null hypothesis, you just say we fail to reject it. And that goes back into this idea that a hypothesis doesn't automatically be accepted as true. It hasn't been proven false yet. And so we never say we accept the null hypothesis. We just say it hasn't been proven false this time, but it may the next time, okay? And so when we get into hypothesis testing, what are the players? What are the numbers that we want to calculate? So this is some familiar vocabulary, but we're going to apply it in a specific fashion. We're going to talk about the p-value. The p-value, and this is a probability value, and you're probably used to that. And we're also talking about a significance level, or the p-value threshold. The idea is this. We're going to go out and collect some data. It's going to be normally distributed, and we're going to have a certain area. And what we did before with confidence levels, like if you had a 95% confidence, that was this region in between here and here, okay? In this case, for hypothesis testing, the p-value is actually the area under the tails. So the p-value is this area. So that's p-value here and here. So if you've got 95%, that means 2.5% is here and 2.5% is here. And what you would do is you'd go out and you'd collect data and you'd have a certain threshold. You'd say, well, in this total, so our total p-value here would be 5%. You may have a threshold and say, we're only going to accept or fail to reject a hypothesis if our p-value is less than 6%, say. And so that's how these two things are going to relate. Your significance level is the threshold of your p-value below which you can reject the null hypothesis. You're going to hear that like 1,000 times, okay? Because that's what we're going to go over this again and again and again. But I'm just trying to give you a little taste of what you're going to see in just a little bit. So p-values, you know this. If the p-value, if that area under the tails is close to 1, then we have strong confidence in the null hypothesis and weak confidence in the alternative hypothesis. So that means high p-values indicate a researcher should fail to reject the null. And so this is bad. We don't want this to happen. We want to reject the null hypothesis. We want to prove the existing theory incorrect, okay? A p-value that's close to 0 implies weak confidence in the null hypothesis. That means the null hypothesis is on shaky ground. The king of the mountain is teetering. And if we have a low p-value, it means that we should probably reject the null hypothesis. And that makes us happy because if we reject the null hypothesis, if we reject the existing hypothesis, if we push the king off the mountain, our hypothesis becomes new king on the mountain until someone comes and tries to push us off, right? And so significance level is the threshold below which the null hypothesis is rejected. So we just talked about that. That is the significance level. So if you set your significance level, let's say at 5%, and then you go out and you conduct an experiment and you collect some data, and let's say that your p-value comes in at 3%, that's going to make you happy. Because if your p-value is less than that threshold, then you can reject the null hypothesis. On the other hand, if you go out and you collect your data and your p-value comes in at 7%, then that is not below your significance level threshold. And you do not get to reject the null hypothesis. And this is going to make you sad. So the king on the mountain stays. You have to go and redo your experiment and see if you can come up with another way to dethrone king on the mountain. Okay? And so this is how these two players interact. The significance level sets the bar. It tells you what measurement you have to come in below in order to reject the null hypothesis. And that's our whole goal. Our goal is to push the king off the mountain. Our goal is to reject the null hypothesis. So everything that I just explained there is outlined here. So p-values less than the significance level, okay, that's this situation right here, indicate that we should reject the null hypothesis and replace the null hypothesis with our alternative hypothesis. Yes, we want that to happen. On the other hand, p levels that are greater than the significance level, which would be this situation, indicate that we should fail to reject the null. And again, we can't say accept the null. We have to say we failed to reject. We failed to push the king off the mountain. That means the null hypothesis stands, king on the mountain stays put, and we need to come up with a new experiment and a new thing. Okay? So this number, this significance level is pretty important. It's an important thing because if we come in at 3%, we reject the null. If our data comes in at 7%, we fail to reject the null. So you might say, well, why don't we just pick a significance level so that way, you know, our numbers come in below it. There's also some ethics involved here, and we're not going to get too much into the ethics. But let's say that you set your threshold at 5%. You say, okay, this is our significance level. So you say our significance level is 5%. And you go out and you collect some data and you analyze the data and you find that you end up with a p-value of 5.2%. Now this is above your significance level. So you do not get to reject the null hypothesis. You fail to reject it. And this is sad, right? This does not make you very happy. So then you think, well, let's go back and look at that data. And maybe there's a couple outliers that you remove from the data. And maybe you massage the data a little bit and kind of, well, these data points actually were this, and let's take these out. And through this effort of massaging the data, you are able to get your p-value down to 4.7%. And now you're below 5%. Now you can reject the null hypothesis. Now you can replace it with your alternative hypothesis. And now you are happy. Okay? What we just did is like completely unethical. That is called p-hacking. It's taking data, and once you realize that the data isn't doing what you wanted it to do, come in under 5%, then you massage the data, you edit out some things, you rearrange it so that way it does come in below, okay? And we're not gonna get into p-hacking and techniques of p-hacking, but just know that it exists. And it's a bad thing. It's very much frowned upon. Researchers can get in some trouble if they do p-hacking and publish the results. And so this is bad. P-hacking is bad. you have to make sure that before you start collecting your data, before you go in and collect your data, that you establish your significance level. What is your significance level? Is it going to be 1%? Is it going to be 5%? Is it going to be 10%? What significance level are you going to establish? And then after you collect your data, you compare the p-value of your data to the established significance level. That's how this process happens. Okay, so what significance level should you pick? You're conducting an experiment. Where do you set that bar for the threshold to reject hypotheses? So we're going to kind of talk about this in terms of Goldilocks and the three bears. And so let's say you set your significance level at 1%. So you're going to say significance level is 1%. Okay, so you're going to run an experiment. You're going to go collect some data, and you're going to say, we are only going to reject the null if our significance level comes in at 1%. So that means for you to reject the null, you have to come in below 1%. If you set it at 1%, this is extremely high rigor. And if your experiment does come in under 1%, it is well respected among researchers. That means you are 99% confident in the null, 99% confidence in the null. So you have a lower probability of rejecting the null hypothesis. So here is a value. This is a p-value of 1%, and this is a confidence level of 99%. You've seen this before. And that correlates to a z-score of 2.576. And so this is your confidence in the null right here. And then this would be your 1% right here, the significance level. And so a lot of times, if you come in under 1%, nobody's going to challenge you. If you say, yeah, we ran our experiment, we set our significance level at 1%, and we came in below 1%. People are going to be like, whoa, that is awesome. You did a great job. Clearly, like beyond a shadow of a doubt, no one's going to challenge this. It's very well respected, okay? That's setting your bar at 1%. Then you could say, well, let's set the bar at 10%. So if you set your significance level at 10%, that means you need to have a p-value that comes in below 10%. And that's not very rigorous. You know, hitting the broadside of a barn, that's kind of what this is. Like, it's easy to do. That means you only have a 90% confidence in the null. So this is only 90%, and that means that you have a 5% here and a 5% here. This is easy to do. So it's not well respected among researchers. If you collect your data and you said, yeah, we came in under 10%, they're going to say, well, who couldn't come in under 10%, right? Like, that's so easy. And so there's a very high probability that you're going to reject the null hypothesis, but then it was easy to do. Like, the data was easy to do. So that's too hot. 1%'s too hot, too rigorous. 10%'s not rigorous enough. So the Goldilocks area is 5%. And this is what we're going to use most of the time. We're going to have a significance level of about 5%. And so this is just right. It's medium rigor, which means it's respected among researchers, not as well respected as 1%, but it's still respected. And you've got a pretty good shot at rejecting the null hypothesis. It's not as good as 10%, but 5% is pretty good. So this is the one we're going to use a lot. Again, here's your 5% broken into 2.5 here and 2.5 here. And then you've got 95% confidence, which is this guy, and that is the area here. And we've got some z-scores in here. You can see the z-score of negative 1.96 and 1.9. And so there is an interval involved here, but instead of in chapter 7, where we were focusing on the area in between the critical points, we're now looking at the area outside of those critical points. That's the area that we're interested in. We're not really interested in this 95% here. We're more interested in these guys, because we're going to take that area and compare it against our threshold. So you've got a 1%, you've got a 10%, and you've got a 5%. So what type of errors could you create? What type of errors are there in hypothesis testing? So these are the test results. And this information here in this column are the actual events. Let's say that the null hypothesis is really true. Okay, let's say that the null hypothesis is true. Okay, and you run a test, and your test fails to reject that true null hypothesis. So that means there is no error. The hypothesis is really true. Your test says that it's true, so there's no error. That's great. On the other hand, let's say that the null hypothesis is actually false, and you run a test, and your test says we should reject the null, that it is false. That also has no error. The actual situation was false, and our test said it's false, so no problem. The problem occurs when the null hypothesis is true, but our test says that it's false. And this is called a false negative. That means the actual situation is true, but our test says that it's false, says a negative. Another situation occurs when the actual hypothesis is false, but our test says that it's true. That's called a type 2 error. And to better explain this, here is a situation involving a pregnancy test. And so in the first column here, the hypothesis is the human is pregnant. So here you can see clearly we have a pregnant human and another pregnant human. So this is true, okay? This is the true column. The hypothesis is true, okay? We also have a column where the hypothesis is false. The human is pregnant, false. And here you can see clearly the patient is not pregnant. Clearly the patient is not pregnant, okay? So now the doctor administers a pregnancy test. So what does the pregnancy test say? In this case, the pregnancy test fails to reject the null. In other words, it says the null hypothesis is true. So the patient is biologically pregnant, and the pregnancy test says you are pregnant. No error. The test matches the biological situation. Everybody's happy. Likewise, we could also have a situation where the test comes back negative and the individual is actually not pregnant. You are not pregnant. So the individual is biologically not pregnant and the test says you're not pregnant. Where we get into trouble is type 1 and type 2 errors. So this is a situation, if we look at this type 1 error, where the person is pregnant, but the test says you are not pregnant. That is a type 1 error. Biologically, the person's pregnant, but the pregnancy test says you're not pregnant. This is a type 1 error. And so this is a case where the hypothesis is true, but the test is false. We can also have a type 2 error, where biologically the person is not pregnant, but they take a pregnancy test and the pregnancy test says that they are pregnant. Congratulations, you're pregnant. This is called a false positive. The test says positive, yes, you are pregnant, but biologically the person is not pregnant. So this is a false positive. And what we want to do is we want to reduce the number of type 1 and type 2 errors. So how do you do that? To reduce a type 1 error, you want to set your threshold at 1%. You want to set that significance level at 1% in order to not have type 1 errors. In order to avoid type 2 errors, you want to set your significance level at 10%. Since neither one of these are really great, again, we talked about this before, 1% and 10%, we're going to usually pick 5% for our significance level. It's going to be right in the middle. So you're going to see a lot of problems using 5% as that kind of the gold standard threshold. And it should also be noted that 5% closely corresponds to 2 standard deviations from the mean. So plus or minus 2 standard deviations from the mean, and we've seen that before. Okay, so let's get into some math. Let's do some math. This is all great that we're explaining this. And by the way, this is the toughest part probably of this whole section, is this introduction to hypothesis testing. Once we get into the math, I think you'll see this is going to go pretty quick. So the first thing you want to do is establish your random variables, establish the mean, and if necessary, the proportion. So we're going to be doing the mean in 8.2 and 8.3, and we'll be doing the proportion in 8.4 and 8.5. Okay, so first establish that for, what is it that you're going to measure? Then you state your null hypothesis. Okay, what is the existing current hypothesis? Either what is the existing mean or what is the existing proportion? And then you're going to pick one of these. So you either say, we believe that the actual mean is less than the null, or that it's greater than the null, or that it's not equal to the null. So you pick one of these. If you do less than the null, then you're going to graph your data. You're going to find a critical value, and you are going to find the area less than that critical value. That is the area that you're looking for. This is your p-value. Okay? On the other hand, if you pick greater than, you're going to graph your normal distribution. You're going to establish a critical value, and you are going to find the area above that critical value. This is for greater than, okay? So this would be your p-value. And if you choose not equal to, you're going to have a normal distribution like this. And when you do not equal to, it's actually the area above and below the critical value. So this is two-tailed. So less than means find the area below. Greater than means find the area above. And not equal to means find the area under both tails. So if you were looking, say, like at 5%, this would be 5%. This would be 5%. And in this case, you've got 2.5% under the left tail and 2.5% under the right tail. So you got to be careful when you have something that's not equals, because you got to remember to divide that area between both tails. Okay? And sometimes the calculations that we're going to use are going to give you the area, 5%, but you got to remember to divide it up under both tails. Okay? And then the second thing you have to do after you pick your null hypothesis is you have to pick your significance level. So you either pick 1%, 5%, or 10%. That's the threshold under which we can reject the null hypothesis. Okay, so go out and collect your data, find your sample statistic, your mean or your proportion, find your test statistic, z-score or t-score, and then find the p-value. And we'll show you how to do this, but we have some tech tools to help you out. Then what you do is you compare these values. So if it's less than, you find the probability to the left. If it's greater than, you find the probability to the right. And if it's not equal to, you find the probability of both the left and the right. We just talked about that. Then you compare them. So if your p-value is less than your significance level threshold, you reject the null hypothesis. Yay! However, if the p-value is greater than your threshold, you fail to reject. Boo, that's not what we want to have happen. And then you write up an interpretation. So let's take a look at this example. So there's a battery company. This company makes batteries, and there's also a pacemaker company. And the pacemaker company needs to buy some batteries. So the battery company claims that their pacemaker battery has a mean lifespan of 500 days. So mu is equal to 500 days. okay, with a standard deviation of 25 days. So sigma equals 25 days, okay? This is for the population. This is population, okay? All their batteries. A pacemaker company intends to purchase $50 million of batteries, but believes that the claim of 500-day lifespan is inflated. And so they want to test the claim before signing a purchase agreement. So what is the null hypothesis? The existing hypothesis from the population says that the average is 500 days. This comes from the population, okay? The pacemaker company is going to submit an alternative hypothesis that the average number of days for the lifespan is actually less than 500 days. If the pacemaker company sets alpha at 1%, then they strongly believe that the batteries don't last as long as the manufacturer claims. So if they're correct, they get to reject the null hypothesis and they should reconsider the purchase contract. If they're wrong, if you set the bar at 1% and you don't come in under 1%, then the battery company could potentially, or the pacemaker company could probably be sued for slander or defamation of character. So you have to consider the consequences of setting it at 1%. On the other hand, the pacemaker company could say, let's set it at 10%. That'll be easy to come in under, right? So if they're right, if they kick the king off the mountain, and that's great, they can proceed with the purchase agreement. But on the other hand, if they're wrong, they may have patients that actually die because they failed to call the manufacturer on their 500-day battery life. So since neither one of these are ideal, they're going to set it at 5%. Okay, so they go out and they get a sample of 30 batteries. So they get a sample of 30 batteries. Here are the lifespans that they tested. And for this sample, the lifespan was 490 days with a standard deviation of 4.56 days. Now, to get the standard deviation, they took the standard deviation from the population and divided it by the square root of the number of batteries in their sample. All right? So that's an important part. You've seen this before, where we take the population standard deviation and divide it by the square root of the number of items. So this is the population standard deviation, or population mean, and the population standard deviation, and this is our sample. We take our population data, and we have a mean of 500 days. So that's our mean of the population right here. There's the mean. Our sample had 490 days mean, and this is our target. That's the value that we're going to set right here, 490. And our standard deviation is 4.56 days. And what we need to know is, what is this area, the area below? This is our p-value. So if this area comes in below 5%, if this area is below 5%, that's good. We can reject their null hypothesis. However, if this area is above 5%, that's bad. We can't reject their null hypothesis, and we have to stick with it. Okay, so that's what all this is setting up. We need to find this area, and it's either above 5% or below 5%. So how do we find this area? And you guys probably have knowledge of how to do this. So the first way we could use is the z-score. So you could subtract the means, which we did here. So this is the sample mean. This is the population mean. You subtract those, and then you divide by the population standard deviation divided by the count of samples. And that gives us a z-score. And then you take that z-score and you go to a z-table. And you go to your z-table and you look up that value and you get this number, 0.0143, which is 1.43%. So that is the area here. This area is 1.43%, which is looking good, right? That is below our threshold of 5%. So that's one way to do it. Look it up in a Z table. What's another way to do it? You could go to Desmos. And so you could calculate a Z-score once again, click on Desmos, and look at the graph. And so here's our standardized mean. Here's our standardized standard deviation. Here is our lower bound, -10, way over here. And here's our upper bound, -2.9. This is our Z-score. And when we do that, Desmos calculates the area under this curve to be this value, which is 1.43%, a little bit more accurate. Or we could use a Google Sheet. And so here's where you put in your population mean, your population standard deviation, and your significance level. Then you put in your sample size and the sample mean. It calculates the sample standard deviation from right here. It calculates your Z-score, the same as what we had before, and it calculates the area below the target and the area above the target, just in case you wanted it. And again, this method tells you 1.43. And my guess is this is probably going to be the method that most of you use. You're going to use the Google Sheet. Okay? So now that we have this, we have established 3 different ways that our p-value, that the area under our target value, down here below, less than, is 1.42%. And that is below our 5% threshold. So that means that we should reject the null hypothesis. So recall that p-value less than the significance level indicates that we should reject the null hypothesis. Yay, we get to reject it. And so that means the pacemaker company should reject the 500-day battery life and replace it with the 490-day battery life. So what should we do? Should we break the contract? Should we say, nope, we're not going to sign it? It's a 10-day difference. Instead of 500, you're looking at 490. And what if the pacemaker company says, well, we expect people to replace their batteries every 365 days. So actually 10 days is not that big of a deal. That's maybe one way to look at it. Maybe the battery company is the only company in town that makes batteries. Do you want to burn a bridge with a company over a 10-day error? So the upshot is, just because a hypothesis has statistical significance doesn't mean it has practical significance. You may choose to go ahead with this contract due to other external factors. The job of the statistician in determining whether or not the 500-day battery life claim is statistically significant is done. You've shown that we should reject that null hypothesis. So that work is done. Now it's up to the PR and the company people to decide whether or not they should continue with the contract. Remember in our first the first exam that we had, where you had to make a recommendation to the professor, the biology professor, about whether or not they should use this new software for their classes. You went and made a recommendation. You showed something statistical about the data, but then it was up to the biology professor to determine whether or not they wanted to buy the software, right? And so that's what this is showing. Kind of the same thing. We've shown some numbers, we've rejected the null hypothesis, but now our work's done. It's sort of up to somebody else to decide whether or not to go forward with this purchase agreement or not.